Welcome to review to the physical science test. We'll go through these questions and look at the answers. So, first thing here, object reaches terminal velocity when a force is acting on it on balance. So the wind resistance equals the force of gravity. Number two, significant digits. These are leading zeros. This is a trailing zero. So we look for a decimal. There's a decimal there. So we've got 1, 2. So the answer is B. Person walks 1.5 miles north, then 1.5 miles south. So 1.5 north and 1.5 south. Every morning for exercise, leaving her front porch at 7 a.m., blah, blah, blah. What is the total displacement of her walk? 0 miles north. Direction doesn't matter because it's 0 miles. Displacement is the distance and direction from your starting location. A person drives 6 blocks north, so 6 blocks north. Then the driver turns west, drives 6 blocks. Then turns south, drives 6 blocks. How could the driver have made the distance shorter while maintaining the same displacement? So your displacement here, if you add these up, your displacement here is 6 west. So this is our answer, driving 6 blocks west from the original starting point. All right. Car traveled 60 kilometers in 2 hours. So we've got distance, we've got time. So we've got 60 kilometers, 2 hours, 82 kilometers in the next 1 hour, and 1 hour, and 68 in the final 2 hours before reaching its destination. 68 in the final 2 hours. So we've got here speed is equal to distance over time. So our distance is equal to 210 kilometers divided by 5 hours, and we get B as our answer, 42.5. Average speed of number 6. What is the average speed of a bobsled whose position versus time graph indicate that it traveled 1.0 times 10 to the second meters in 25 seconds? So we've got the speed equals distance over time. It's equal to 1.0 times 10 to the second meters in 25 seconds. So that's 100 meters in 25 seconds. So your average speed is 4 meters per second. Next, in the position time graph below, the little dude responsible for this motion. All right, so let's go ahead and take a look at this. Let's pretend we don't know these other questions here. Has an average of speed of 10 meters per second over the time shown. Well, over 10 seconds, they're going 10 meters, so the speed is equal to 10 meters over 10 seconds, so the average is equal to 1 meter per second. So we know that's not true. Is moving for the constant speed for the entire time shown? Well, if they were moving at a constant speed, this slope would be a constant slope, a straight line, and is moving with 0 speed for the entire time. Well, if they're moving with 0 speed, they would stay in the same position. So we know that's not correct. So is accelerating the whole time, and the exponential growth here, the curved line, indicates acceleration. All right, car is turning around a corner at a constant speed. Which of the following is true? Velocity is constant. Well, velocity is speed and direction, so it's turning, so the direction is not constant. Car speed is changing. Well, it tells us right here, constant speed, so we know that's not true. Car is accelerating. Well, accelerating is the change in direction or speed. So, or, right, where accelerating is a change in velocity, and if you're changing direction, you are changing velocity. Which of the following of the physical quantities is not a vector? The answer is distance. Displacement is a distance in a direction. Velocity is a speed with a direction. Force is the size of a push or pull in a direction. And acceleration is the rate of change of velocity in a given direction. Because the acceleration, if it's positive, you're essentially going forward. If it's negative, you're going backwards, or the rate of change is negative. Newton's second law of motion is F equals ma. So the force of an object is equal to the mass of the object times the acceleration. Which of the following relationships is correct? And number 11, all right, 1 Newton equals 1 kilograms times meters per second squared. All right, that's just a little bit of a different way of looking at it, but it is it's equivalent when it's written that way. Which of the following frictions increases as the speed of the object increases? This is fluid friction, right? So stale friction, I think that's just made up. Static, it goes away because the object's moving. Sliding, we've looked at that a bit. Sliding stays pretty constant. Fluid friction, this is air resistance, and also through liquids. As you move faster, that increase. Which of the following affect the motion of a leaf falling from a tree? Gravity and fluid friction. So this is the best answer because centripetal force and static friction, well, that's static friction. We haven't even, this is moving. It's a motion of a leaf that's falling from a tree, so it's not static friction. Sliding friction and air current, well, it's not touching an object. Just gravity, well, it's got air resistance as well. Don't forget that air resistance is a type of fluid friction. So that is correct. Gravity is correct. Next, when an unbalanced force acts on an object, so this is Newton's first law of motion. The object's going to keep on doing whatever it's doing unless an unbalanced force acts on it. So here you've got, it's going to accelerate, it'll speed up, slow down, or change directions, or any combination of those. Well, it wouldn't speed up and slow down. The inertia of the object, it's not going to change its inertia. Its mass isn't going to change. It doesn't affect gravity, and the object's motion would have to change. An object that has twice as much mass as another object also has twice as much inertia. Inertia and mass are the same thing. An object weighs 30 newtons on Earth. A second object weighs 30 newtons on the Moon. Which object has the greater mass? Weight is equal to mass times gravity. So if we go to if we're on Earth, we've got 30 newtons is equal to gravity times some mass. And then on the Moon, we've got 30 newtons is equal to some mass times gravity, but we know that the Moon's gravity is smaller. All right, so I've written the Earth's gravity as a capital G to represent that that's bigger. The Moon's gravity is lowercase g to represent that that's smaller. Well, if we've got a number times a bigger number and a number times a smaller number, well, this will have to be bigger to compensate for this being smaller and equal 30 newtons. And this will have to be lower, so the mass is, the greater mass is the one on the Moon. $10 Newton and $1 Newton block lie on a horizontal frictionless table. To push them with equal accelerations, we would have to push with 10 times as much force on the heavier block. So this is equal to F equals ma. So if we've got a 10 Newton force is equal to mass. The accelerations, it doesn't give us a value. We just know they want the values to be the same. So we could say mass times, well, let's just say we're going to do 1 meter per second for the acceleration. And then we have 1 Newton is equal to mass times 1 meter per second. So here we've got two equal accelerations. We've got our two different forces. Well, in order to get this balanced out, this right here has to be 10 kilograms, and this has to be 1 kilogram. So we know that the heavier block right here needs 10 times as much force. All right, this is a block right here. This is a block. All right, James used two different balances to measure the mass of a rock. Balance A read 6.7, balance B read 6.682, which of the following is definitely true? Well, balance B is giving us more digits here, so that is more precision right there. We know that for sure. Accuracy, there's not enough information to tell about accuracy, so we don't know for sure that that's true. Balance B is more precise and more accurate. Well, again, we don't know that this is true, so obviously we can rule this one out as well. It's not none of the above because balance B is giving us more digits there, so that's more precision. Next, scientists consider significant figures when performing calculations with measurements. Well, remember that your calculator makes up values past a certain number. So if you put in your calculator 6.2, well, your calculator just goes ahead and assumes that it's 2000. If you're finding the mass of something and you find the mass of something to be 6.2 grams, well, you don't know what the next digits are. So if you start using zeros when it could be a 4, you are going to give inaccurate numbers. Derived unit is a 2 or more base units put together to make a more complicated unit. Meters is just a single base unit. Centimeters is one base unit and a prefix to describe it. Inches isn't even a base unit, but it's just a measurement of length by itself. The equivalent would be meters in metric. And newtons is kilograms times meters per second squared. So within this unit, you've got kilograms, you've got meters, you've got seconds, and you have seconds again. So you have 4 base units in this one derived unit. Next, Newton's laws. Meteor moving in a straight path changes direction when it flies by Earth. So it's going to keep on doing whatever it's doing until it's acted on by another force. Changes direction when it flies by Earth, so that's implying that Earth's gravity has acted on it. So that's the first law. A full grocery cart that is pushed starts moving and increases speed, but the same push increases its speed even more when the cart is empty. So you're talking about acceleration. It's got to accelerate more. So F equals ma. If it's full, your mass is bigger. If it's empty, your mass is smaller. Right, that's the second law. A skydiver fell at terminal velocity until opening her parachute. Well, she's going to keep on moving she's got balanced forces on her. Terminal velocity is where air resistance and gravity balance out. So she's got balanced forces acting on her until she opens her parachute. That increases the air resistance, so her velocity is going to change. That's the first law. 0.213 grams. And we know in our unit multiplier we're going to want 1,000 grams in the bottom, so we can cancel this out. 1 kilogram. Alright, so we will go ahead and cancel our unit out, and then we end up with 0.213 divided by 1,000, 0.000213 kilograms. Convert 75 centimeters to millimeters. A lot of people had a hard time knowing how many centimeters or how many millimeters are in a millimeter. You know that centi is 1/100th, and a milli is 1/1000th. So the millimeter is 10 times smaller. You might also think back to a metric ruler where you have centimeters and then the millimeter tick marks in between, and you should know that there's 10 there. So we would do 0.0075 centimeters to 1 centimeter has 10 millimeters. Cancel, multiply, 0.075 millimeters. Next, convert 600 millimeters cubed to centimeters cubed. Alright, well, we did this conversion up here, so we're pretty comfortable with that. So we've got 600 millimeters cubed, or another way to put that is 600 millimeters times millimeters times millimeters, right, is going to be multiplied by, we'll have 10 millimeters per 1 centimeter. Well, here we cancel out one of them. So let's do it again. 1 centimeter to 10 millimeters. Cancel the second one. And 1 centimeter to 10 millimeters. And we'll cancel the third. So we just then solve this problem. We see that we have 600 divided by 1,000, which equals 0.6. Our unit is centimeters times centimeters times centimeters, centimeters cubed. Convert 1.2 nautical miles to meters. So we've got 1.2 nautical miles, and we want that to meters. Well, I'm given this conversion factor. It says 1 nautical mile is 1.85 kilometers. So we have 1.85 kilometers over 1 nautical mile. And we'll go ahead and cancel this, multiply together. You should get that it's 2.220 kilometers. And we know that there are 1,000 meters in 1 kilometer. So we'll cancel this out, and we get 2,220 meters. Scientific notation. Whenever you're dealing in scientific notation, the coefficient only has one number to the left of the decimal. So it should be 3.42 times 10 to the negative third. And this one should be 3.850 times 10 to the sixth. The little dude has a mass of 1.5 kilograms. What's the weight of the little dude on the surface of the Earth? Write the equation for finding weight. Is mass times gravity. Find the weight in newtons. The acceleration due to gravity is given to you right there on the sheet. So we have our knowns are that the mass equals 1.5 kilograms, and we're given gravity equals 9.8 meters per second squared. So 1.5 kilograms times 9.8 meters per second squared gives us our weight of 14.7 newtons. If this little dude went to the moon, would the acceleration due to gravity is 1.6 meters per second? Would his mass be the same as Earth? Well, you're talking about mass. Mass is the amount of matter in the object, and mass doesn't change, right? It's the same little dude. There's the same amount of matter that makes him up, has the same number of fingers, presumably, and toes that he did before. So his mass, yes, right? Mass depends on the amount of matter, not gravity. Weight depends on gravity. The distance between the sun and the earth is 1.5 times 10 to the 11th meters. Sunlight takes 5.0 times 10 to the second to reach Earth. What's the speed of light? Speed equals distance over time. So you've got 1.5 times 10 to the 11th meters over 5.0 times 10 to the second seconds. So to divide the scientific notation, you can use your calculator. That's perfectly acceptable. If you want to do it by hand, I would recommend changing this into 15 times 10 to the 10th meters. So we've brought one of our powers of 10 over and moved the decimal over, divided by 5 times 10 to the second seconds. And then so that's going to equal 15 divided by 3, times 10 to the 10 minus 2, 8 meters per second. You could also just do that on your calculator. That would have been fine as well. This one, pretty simple. I told everybody that I forgot this here. The initial speed was 0 meters per second. Acceleration is 3.00 meters per second squared. Time is equal to 30.0 seconds. The bonus right here, a lot of people who tried this got this right. The distance is equal to velocity initial, which is 0. So 0 meters per second times time, 30 seconds, plus 1/2 the acceleration, which is 3.0 meters per second squared, times time, which is 30 seconds, squared. Make sure you do your order of operations. Some people were multiplying this and then squaring it. You've got to do your order of operations. So parentheses, exponents, everything within the parentheses is already simplified. So we do our exponents. So this right here would simplify to 900 seconds squared. Then you can go ahead and multiply this out. This will cancel here. This will cancel here. You've got 3 times 900, which will equal 2,700 meters times 1/2, which is 1350 meters. All right. right, the river problem. Everybody loves the river problem. Um, this one was actually pretty challenging for a lot of people. I think that it was important to make sure that we did a bunch of, we did the review problem with the airplane, flying the jet south. We did that in class and went over. A lot of people also asked about some of the practice sheets. I had a couple of problems like this in the practice sheets to work on. So how long does it take the little dude to get all across this river? So the river is 50 meters wide, 50 meters right here, and the little dude um, is swimming at 3 meters per second, and he aims directly south. So he's got a velocity of 3 meters per second south. The river carries him 2 meters per second east. So these are the two components of his velocity here. He's heading towards the south bank at a speed of 3 meters per second. Right, that's most important. This velocity right here won't affect how long it takes him to get to the south bank if he aims directly south and swims at it at a rate of 3 meters per second. So we need to find the time that he is going to take. So we know that speed equals distance over time, which would equal, we could simplify this or solve for time beforehand. So time would equal distance over speed, which would equal 50 meters over 3 meters per second, and that's going to equal 16.6 seconds is our time. How far does the current push the little dude downstream while he's swimming? Well, if he's swimming for 16.6 seconds and the current is pushing him downstream at 2 meters per second right here, that's our speed. That's our speed, that's our time. So we need to solve for distance. Distance is equal to speed times time, which is just this equation, solve for distance. And that's going to mean that it is equal to 2 meters per second times 16.6 seconds. And so our distance is going to equal about 33.3 meters. Next, to an observer on a nearby cliff, how fast does he appear to go? So the observer is going to see both components of his velocity put together. So he's going to see the little dude swimming south at 3 meters per second and getting pushed downstream at a rate of 2 meters per second. So you have to use the Pythagorean theorem to solve for your resultant vector. So it's 3 meters per second squared plus 2 meters per second squared. That we'll square the numbers because we don't want to change these into accelerations. So we've got 9 meters per second plus 4 meters per second equals c squared. 13 meters per second, and we want the square root of 13 is equal to c squared, square root of both sides. Will get you c, and c equals about 3.6 meters per second. How much distance does he cover? So How much distance does he cover? Well, we know that the distance is going to be the resulting displacement of the 50 meters across plus our answer from B, 33.3 meters downstream. We use the Pythagorean theorem to solve this, and we get that our answer, I believe it's about 60 meters. So 50, you solve this out, you get the answer is about 60.07, or we could just round to 60 meters. It's covered because that is how far he's actually moving. He doesn't go down and then over. His path across the river is going to be a diagonal path, and we want to know how long that path is. And we use the Pythagorean theorem to solve that. Next, tow truck driver exerts a net horizontal force on the car. So force equals mass times acceleration. You could also solve it for acceleration. Acceleration equals force over mass, which is equal to 1125 newtons over 724 kilograms. And that is going to equal about 1.5 meters per second squared. Last page. This is a two-step problem. A small engine causes a 0.2 kilogram model airplane moving at 9.5 meters per second to accelerate to 11.8 meters per second in 2.3 seconds. What's the net force? So we know force equals mass times acceleration. We have the mass. We need the acceleration. Acceleration is going to equal velocity final minus velocity initial over change in time. So the acceleration is going to equal the velocity final, 11.8, minus, let's go ahead, meters per second, minus 9.5 meters per second, divided by change in time, 2.3 seconds. So the acceleration, solve that out, is equal to 1 meter per second squared. So the force is going to equal 0.2 kilograms times 1 meter per second squared. So it's going to equal 0.2 newtons. Last one here, sum these forces. So this one, there's only one force, so we'll sum it. So it's 4 newtons. You could say to the right, you could say east, you could say positive. Here we've got 8 newtons to the west plus 4 newtons to the east equals 4 newtons. This way you could say the left, you could say the west, you could say negative. Here 3 and 3 balance out, 0 Newton force. Here they add up together. So you've got 5 newtons, you could say to the right, you could say east, you could say positive.